Gibbons are able to move quickly from branch to branch. By picking up their legs, they change their moment of inertia, enabling them to gain momentum while swinging. The act of continuous swinging is called brachiation. Brachiating robots demonstrate how lower appendages can be used to achieve continuous swinging motions. Robots have also been designed for in-air reorientation using similar mechanisms of lower body control. Currently, there exists a gap that combines swinging motion with reorientation. The goal of our research is to show how robots can utilize lower appendages to gain momentum while swinging to launch and then reorient in the air. To address this goal, we want to answer the question, how does changing the moment of inertia in swinging robots by using their lower appendages enable different launch trajectories and orientations?
In order to best test our research question, we decided to create a 3-link swinging robot with our bottom 2 links serving as a tail. To design the robot, we went through material selection and topology optimization processes in order to concentrate our mass in our tail. The 2 links in our tail allow our robot to complete several different motions. We can move our motors in opposing directions to lift the tail directly upwards. We can also move our motors in the same direction in order to swing the robot's momentum. Finally, we can hold our lower motor in place to treat our robot like a traditional single-link tail. This allows us to see how the additional link changes our performance when both swinging and reorienting midair.
The design parameters of our robot, such as the lengths of each segment, were determined using a MATLAB simulation. For a variety of different length ratios, simulations were run to determine which would enable the robot to swing the fastest. In this way, a set of final design parameters was computationally determined. Simulation was further conducted to compare the swinging performance of a robot with 3 lengths as well as one that has been fixed, reducing its range of motion to 2 lengths. The 3-link robot, with its increased ability to change its moment of inertia, was able to achieve faster swing speeds while using less energy compared to the 2-link robot. This is in direct contrast with the simulations determining reorientation ability, which found that reduced links increased robotic performance. When dropped from a vertical orientation and tasked with swinging the air to horizontal before hitting the ground, the 2-link robot used less energy over the same time span.
A deep neural network agent was trained using reinforcement learning in the MATLAB simulation. This provided the control for the robot motion. Due to the inherent chaotic characteristics of the system, the learning agent was trained using the 2-link system to reduce the sensitivity of the training simulation.
A total of 6 drop tests were performed using the prototype, 3 in the 2-link configuration and 3 in the 3-link configuration. In the drop test, the robot uses the releasing mechanism to drop from the bar and then try to achieve a maximum angle of rotation during the fall. The 3-link configuration achieved a greater rotation during the drop than the 2-link configuration. After we modeled our robot in simulation, it was time to test. We ran 1 swing test on the 2-link configuration robot. An IMU was used to collect experimental data during testing. The 2-link feed-forward trajectory generated by the deep deterministic policy gradient agent allows a basic swing up. However, it can be observed that the amplitude of the swing is just less than half of the expected amplitude. Likely causes of this include the feed-forward nature of the control being applied, as well as imprecision in the modeling of the system. After we evaluate swinging, we turn to launching, where our robot was capable of launching forward 3 feet. This is still early testing of launching, and in the future we would like to be able to reorient while launching. We would also like to be able to catch ourselves at another bar.
In summary, we built a 3-link robot capable of mimicking some of the swinging and reorientation behaviors found in Gibbons. We found that the additional motion capabilities of the 3 links makes it more effective and efficient at swinging than a 2-link robot. We also found that a 3-link configuration can reorient mid-air quicker than a 2-link configuration, but is less efficient with respect to energy used.